I will start with a brief recollection of yesterday, and then we'll prove something. So we are talking about finite Coxeter groups. There is some finite set of generators. We have relations that are given by this list of numbers, this matrix of numbers. This gives us some group, and we want to understand when is this group finite. This was sort of what we talked about. And then we define the matrix. So the diagonal of the matrix is 1. And then we define some matrix with some numbers. The numbers on the diagonal are 1. Off the diagonal, they are 0 or less. And the claim we had is that if G is finite, this was the main lemma, then this matrix is positive definite. This was the main thing we wanted to prove. And then we saw how it completes, it gives us some information, some sort of combinatorial information. So the point of today is to prove this. So our goal is to prove this statement. There is some matrix and it is positive definite. And maybe the most important lesson, at least for me, is this is a sort of a being positive definite says that there are many things that are positive. Yeah, we put x here, we put x here, we get positive. We put some other x here, some other x here, we get positive. So this is like a lot of calculations, and we need to understand how to do that. And this is sort of intimidating. How do you prove that something is always positive? And then the lesson is that we have some symmetries here. We have a group that we can use. And then out of all possible positive definite matrices, we sort of think in our minds there is some symmetry here. So the symmetry sort of glues together things. So sort of if there are many things and there is some symmetry, so these two things are actually the same. So in the proof we'll see that out of all possible options, there are many things, and actually all of them are just one. There is one single option for this matrix to be, and because there is just one option, it must be positive definite. Okay, so there is no calculation, it's just in our minds. That's quite amazing. Okay, so now let's do that. The proof uses a representation theory, and I will say everything. I hope I will get to the end, actually. So let's see how it goes. So we have this involution in an algebraic setting, and we define a map from involutions. So this is one element, algebraic, and we make it into linear algebra. So we define a linear map, which I will denote by rho S. It's a linear map. It takes a d-dimensional vector, and it is as the reflection that S defines, but with the inner product defined by Q. Okay? So we saw that there is a formula for reflection in Euclidean space, where we use the standard inner product. Instead of the standard inner product, we put this sort of quadratic form. Okay, so that's a linear map in X. So that's the first step. So maybe as a comment, so we define it just for these involutions. We don't do it for the whole group. just take a generator, define this matrix or linear map. This generator, define this linear map. Okay, so we have now a collection of D linear maps. And maybe the first claim, which I will say just a bit about, is that these linear maps, they satisfy the same relations. Okay, so what does it mean? For every S and T in S, they satisfy the same relation, these linear maps. Okay, so that's one part of the proof. So we have linear maps, we can compose linear maps, and then the claim is that they satisfy exactly the same list of relations as the original sort of abstract involutions.
And not with a smaller m, that's right? Like with that one?
Yeah, with that specific m. Okay, so that's a claim, and the proof of the claim is has two parts. So I will not prove all of it, but I will just sort of indicate how maybe we can prove that. So it has two parts. Part number one says that it's enough to look on the action of these linear maps on the span of just these two unit vectors. So that's step number one. We have a d-dimensional space, but in fact it's enough to look on a two-dimensional space. That's step number one. It's not a hard step, but I will not do it. I think there are more interesting things. And the second step, this is a two-dimensional problem, so it's some calculation. Okay, so that's sort of the high-level structure of this proof. Does it make sense? Okay, so that will be the proof for us. Each of them is an exercise. So maybe not a very easy exercise, but
enough for what?
To prove the claim. So the action outside of the span is just by identity. It does nothing. That's sort of the... Okay. So that's claim number one. And this is a very informative claim just because of this corollary. So what do we... so we have a group G. It's a sort of abstract group. And we know it's finite, or we assume it is finite. So now we have also a collection of linear maps, and we can look at the group they generate. You just compose them again and again and again, and you get something. Because of the claim, so I'll denote by R this group, the group generated by these linear maps. Okay? So because these satisfy the same relations, we immediately get that the group R is finite. Yeah, the same relations, smaller group. So that's the only point where we are using that claim. Okay? So from now on, we will focus on R, not on G. It is interesting, if you want to understand things better, to understand the relationship between R and G. This is not very easy. So they are isomorphic. Yeah, but it's not a very easy thing to prove. It's a quotient. Yeah. Okay, so that's step number one. Now the main idea of sort of gluing this space together, so we had many possible matrices, and all of them are the same, is based on this irreducibility idea, which is a very... So this is a very important and basic idea. So we will have a vector space, and we will work with complex numbers instead of real numbers. The reason is that over the complex numbers, every matrix has an eigenvalue, and this will serve us later. So we work with this vector space, and these linear maps act in this vector space. And so first, what is an R invariant subspace? So we have a subspace of V. It is R invariant if, when we apply a linear map in R, we stay in. Okay, so this means that the subspace is R invariant. We act with these linear maps and we don't move outside. And R irreducible, we say that V is irreducible. Yeah. If for every I'll write non-trivial R invariant U, if there is no, if maybe I'll write it, if every R invariant U is trivial, meaning either 0 or V. Okay, so this is being, the whole space is irreducible. This is a definition, important definition. If we look on some R invariant subspace, it's either 0 or everything. There is nothing in between. This is irreducible. And the main thing we want to prove to begin with, so maybe I'll write it as a proposition, is that if this graph gamma, the graph whose edges indicate that the elements do not commute, if gamma is connected, then V is irreducible. Okay? So that's the main proposition we are going to prove now. And there are two parts to this proof. One part depends on gamma and Q and so forth. And one is sort of very abstract, and I'll try to explain both. V is it's the complex numbers with D coordinates. Linear subspace.
Linear subspace. Okay.
Yeah, no topology. Yeah. Okay, so this is the main, the main thing. So we have two parts. The first part is a claim, and this is very specific. So the claim is like this. So we assume that this graph is connected, and we have a sort of a subspace that is R invariant, but it's not everything. Okay, so we have some R invariant subspace, and it's not everything. Then this subspace is part of a very special collection. So I'll denote it by the zeros of Q. So these are all the points, so that if you plug them on the left-hand side on Q, then it's basically the zero map. I didn't write the 0. In V, sorry. Yeah. Sorry, it was two typos in the same line. Okay, so this is very specific to this question. we have a connected graph, we have an R invariant subspace, then it is a subset of a very particular linear space. Okay? That's the U is any R invariant subspace, which is not V. Yeah? Okay. And the proof, so this is what we want to, the first claim. So maybe I'll start here. So the proof is first maybe do an observation. So for every S, there are two options. Either it is part of U, or, so one of the two things must hold. The other thing is that when we take sort of the measurement with respect to U, we get 0. Okay, so this is the first observation. There are two options. Either some element is in U, or it sort of nullifies this quadratic map on U. And the reason is very simple. So maybe I'll write it here. So if this is non-zero, so we assume it is non-zero, and we look on this, what happens when we act on X with rho of that S. So because U is invariant, this is a point in U, some point in U. On the other hand, this is equal to X minus some number, which is non-zero, times ES, which is also, so ES is in U, X is in U, yeah, so we assume X is in U, this is in U, this is in U, so this is in U because this is non-zero. So this is the reason for this property. Okay, so it's a very simple property. So here the discussion is on the other in the standard basis because the information we have is that the graph is connected. So we have information about sort of these specific unit vectors. Sure. So the point is that because U is invariant, when we act with rho of that specific S, we stay in U.
Yeah, that's
so if this is a non-zero number,
can you write equals instead of greater than?
it's equal. It's just my very yeah.
okay, say
If this is non-zero,
wait, it's an if ES is in U, then something, or what?
one of these two things holds.
This or that.
Okay.
So one of the following holds.
Okay.
So this is general. Now let's use it. So now we have, let's say we have some element in T and some element in U and some element not in U. So now we are trying to get to this gamma. So if we have one element inside and one element outside, this means that this is 0. Right? This is just follows from what we just saw. So so this is outside, so and this is inside, so this is 0. So this means that whenever there is one element in U, one of the ETs in U, and one is outside U, there is no edge between them. So we can collect all the ones in U on one side, all the one outside of U on the other side, and there is a cut. It's sort of not a cut, there is nothing. So it's not connected. So this means, because gamma is connected, we can conclude that ES, and we know that not all of the ESs are in U because U is not everything. none of them are in U, which means that U is empty, not empty, 0, so it's a subset of this thing. This is sort of the part where we use the information. I'll just delete this is now behind us. So we start with a connected graph and we deduce some algebraic condition. That's part number 1. Okay, the second part, this is called Maschke theorem. So I'll give it a, so it says that if U is R invariant, then there is a complement of U. I'm not sure what is there is, that is R invariant, and V is U direct sum U complement. So this is a very general statement. When we have an R invariant subspace over, say, the complex numbers, we can complete it to the whole space in the direct sum sense using an invariant subspace. R is finite, yeah. Let's prove, I think we'll have time to actually prove it. So let's prove this at least in a high level. I'll give you the main idea. So first we take this V and find something that makes it the whole V. Yeah, so we complement U by something. And then we define a projection from all of V, so this is U, to U. So we take a vector in all of V and project it to U in this sense. Okay, just delete W. And now we make this projection symmetric, and this is where we use the fact that R is finite. So we define a projection. So this is the main define. A projection, which is we take a random element in this group and conjugate this projection with it. Okay, so that's the main step. So we have something non-symmetric, we make it symmetric. And now the complement of U is the kernel of this projection. So there are two things to verify. First is that the complement is actually a complement of U in the direct sum sense, and that it is R invariant. That these are two things. So the fact that it is R invariant just follows from this construction because P commutes with a group just by construction. So this is R invariant because P commutes with every single group element, and it's just a calculation. The sum, instead of being in this order, is in this order. P0 is this specific projection. We take a vector in the space, small u and small w, and delete w. Yeah? And for the second step, we need to do the direct sum. So we need to show that the intersection is 0, and we can represent every vector in this way. So to do that, we know that if we look on this, so this is V, not U. We take any vector and apply P twice, we get a fixed point. So P of V is in U, and P on U is identity. Yeah, because the two R's cancel. So this is true for every single vector in the space. So now we take a vector and write it as V minus PV plus PV. This is in U, because it's a projection to U, and U is invariant. And when we apply P to this, we get 0. because P of V is P of V and P of V is P of V. So this is in U complement. Yeah, and by construction, this is the kernel of P, and U is not in the kernel of P. So the intersection is 0. So this is sort of the proof. Okay, so these are the two steps, and now we can prove this proposition. So it says that if gamma is connected, then V is irreducible, R irreducible. And the proof is now very simple. So if U is a subspace of V, is R invariant, so we let U be R invariant, then we have the complement of U, which is also R invariant. This is by Maschke theorem. Yeah, R is fine, yeah. I assume throughout that the group G is fine. Yeah, I didn't write it everywhere. Yeah. Then U complement is R invariant, which means that both U and U complement is a subset of this. This is this claim. And what is this thing? It's the collection of all x's, so that again, I didn't write this. The sort of left kernel, yeah. Yeah. Mm-hmm. V. Yeah, this is just a fixed space. Yeah, just the kernel. So we have, this is a subspace and this is a subspace, so, and the direct sum is everything, which means that V is in this thing. But it's very easy to see that it's not. For example, E of S is 1. So it's not true that it's the zero map. So this means that U is trivial, so there is sort of no U complement. Okay? So this is this proposition. So this was sort of general, very general. A very important definition is this irreducibility. Now for the last part of the proof, so the title is All Forms Are the Same. So that's the last part of the proof. So we have Q, we have this irreducibility property, and now we want to say that Q is not different than any other form. So there is a form which is positive definite, so Q is positive definite. That's the proof. Let's start by saying what is the property. So maybe I'll write it as claim number 1. Q is R invariant. What does it mean? That Q of Rx, Ry is Q of xy for every R in R and for every xy in V. Okay, so that's being R invariant. And this is a very simple calculation. So maybe I'll just write one point is that we can verify, it's enough to verify on these specific linear maps, rho S, not on every R, and rho S has a very simple formula, so we just substitute it and see that it works. So this is a very easy task. It's 2 lines, which I will not do. So that's the property that makes this Q special, or that allows us not to calculate anything. So instead of Q, let's do something that we can easily understand. So let's define another linear map, another quadratic form. So I'll denote it by E. And this is the symmetric version of the standard inner product. Okay, so this is the standard inner product over the complex numbers.
This is not an average?
Yeah, we can, yeah. Here it's, we can do an average, doesn't matter. So here is another form. There are two obvious things about this form. One is that it is positive definite, because the standard inner product is positive definite and all the matrices are invertible. So nothing strange is going on. And the second, that it is R invariant. And this is again because we just put the whole sum here. So the claim for E is that E is positive definite and R invariant. So this is the point which we, in this space of forms, which is very easy to understand. And now we will use irreducibility to show that Q and E are the same. That's the proof. So we have two more claims. The first claim is using this irreducibility. So the claim is like this: if V is irreducible and B is some linear map that commutes with R, then B is a scalar. This is sure.
Yeah, sure, that has a name.
Yeah, like this? Did I? Yeah.
Yes.
So this is Schur's lemma. So yes, scalars commute with everything, and if we have an irreducible thing against it, then this is the only thing that can remain. So this is, and here we need the complex numbers. This is the point where we need the complex numbers. So proof B has an eigenspace U with eigenvalue, let's say lambda. Okay? So this is complex numbers. Is it okay? Because B commutes with R, this subspace is R invariant. This is just a simple calculation. So U is R invariant because B and R commute. So if we have a vector with eigenvalue lambda for B, then R of that thing is the same, is also an eigenvalue. Eigenvector is the same eigenvalue. And because V is R irreducible, this means that this is a non-empty subspace. This means that U is everything. So it's not zero, it must be everything, and this is it. Okay? So lambda is this constant that we were looking for. So this is Schur's lemma. And now the last claim, so the final claim, let's call it another proposition. If gamma is connected, then there is a positive constant such that Q is CE. Okay, that's the final step. And now we are done. E is positive definite, so Q is positive definite. Okay, so now the final step. So we know gamma is connected, so we know that V is irreducible. This is one of the previous proposition. So we can use the Schur's lemma later on. So now here is the, so because E has full rank, meaning so as a matrix, there is some matrix B, so that we can write this. So I'll write it here. We can look on E of Bxy, and this is equal to Q xy. Yeah, we can make E into Q by some matrix. There exists B. For all xy, yeah.
Let's just roll first, right?
Yeah. So Q could be the zero matrix, or Q could, it's, yeah.
Just roll operations.
Yeah, so now we want to prove that B commutes with R. That's what we want to do. So we know that they're the same. So how do we do that? We look on E of B, R, X, and Y. So we chose some R and we applied this thing. This is equal to Q of R, X, and Y, just by what we just wrote. Now we can move R to the other side, because Q is R invariant. And now we can add E again. And now we can move R to the other side. So we sort of see that R and B commute. It's still, we need to pull it out. It's not written explicitly. So.
Every X and Y, so it should be, right?
Yeah, so I'll actually do the whole thing. So now for every X, let's Y. So if we move this to the other side, we see that BRX minus RBX, when we take Y on the other side, we get 0. So we can choose Y to be this thing. We first choose X, and then we choose Y to be this thing, and then we see that Q of Y and Y is that, E of Y and Y is 0. Right, this is just, we move this to the other side, we get 0, and then we have Y inner product with Y, or with E, Y, Y. Does it make sense? So Y is 0, because E is positive definite, which means that BRX is equal to RBX for every X. So R commutes with B. Which now by Schur's lemma tells us that there is a constant that B is, let's say, lambda, some constant. This is Schur's lemma. Okay, so now the only thing to understand is this lambda, so we just substitute one of the E's. So E of SS is some positive number, and Q of ES is 1. So we get that this lambda must be positive. And this is it. We proved this. What is written here, maybe in some other way, is, I'll write it like this. X transpose, B transpose, E, Y is equal to X transpose Q, Y. Yeah, we choose B transpose to be so that B transpose times E is Q. So, yeah, so we can do. So B transpose is E inverse Q. Sorry, on the other side. Q E inverse. So this is it's not, I didn't, just this transpose and inverse, just you need to concentrate, so I wanted to avoid it. But yeah, so the point is that E is invertible, so we can do whatever we want with it. This is the point. Okay. So this was, all of this was Coxeter's ideas, and there is a huge theory that I didn't talk about. So you see all of these, there is Maschke theorem, shoes, so this is part of a huge thing. I think it's a very, very nice demonstration of the power of this language. It just exactly hit the point, this so you can prove things without any calculation, just by thinking. And so this is one amazing thing. So maybe I'll just summarize. So in my mind, there are two sort of high-level takeaways. So remark. So one thing is we started with this, like this type of question, and we wanted to understand all such groups in general, all such finite groups, and the proof shows that the only thing you need to do is show that something is positive definite. This is all the information you need, which is quite amazing. So this information allows to classify all such groups. It's sort of just all information is hidden here in this sort of numerical statement. We saw two corollaries, not all of them. But yeah, this is the one amazing property. And the second is that you can prove this with no calculations. Yeah, it's sort of by thinking, which is another amazing thing. So actually, maybe I should write here all information on G. So maybe if G is finite, all info on this group is here. This is sort of what I want to indicate. Even when we know it is finite, this hides all combinatorial information, just this one numerical statement. So we had this kernel, this Z of Q, and we needed it to contain every irreducible. So that's where connectivity is important. Yeah, it's a very rare. Yeah, maybe just as an exercise in drawing. So if you write in Google finite Coxeter group diagram or some version of this, you will see many diagrams, or like, how do you call it? I think Coxeter called it a table. So the actual gammas, so this is one possible gamma, just a path. So there is some, he has some symbol notation which I don't understand, maybe you understand it. Yeah, exactly. This is the symmetric group. It's hard to see it, but this is the symmetric group. There is a similar picture. So every such arrow indicates 3 if there is no number. There is one more with where the last one is a 4. That's another option. One other option is a pair with any number. 3 generators with a 5. 4 generated with a 4. 4 generators with a 5. And there is 4 more pictures. And that's it. This is hidden in the fact that Q is positive definite. This list of options.
So there is some option with the 3?
Yeah. So maybe I'll do the last one is 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 1. This is a group of size. I don't know how to say this number. Let's start here. So there is a 600 and then 70. So this is the size of the group. Thank you. I hope it was interesting. If you want to talk more, I'll be happy to.